Okay, so welcome to session 3C, which is on fiber optic technologies. We have two main subjects. Presentation of two test beds, the VIOLA test bed by Peter Kaufmann from DFN, and the European Union MUPBED project with Henrik Wessing from the Danish Technical University. And last, we have a presentation from a commercial company, Corning, who is basically the inventor of fiber optic cables, and it will be given by Sergey Ten. Okay, so let's start with Peter Kaufmann.
Okay.
Everything here?
Okay, thank you, Olivier, and welcome to the first talk this afternoon. In my talk, I will present you the German testbed VIOLA. VIOLA stands for Vertically Integrated Optical Testbed for Large Application. At first, we had another name, and this was already occupied by somebody else, and so we had a long discussion about a proper name. I think VIOLA finally sounds well. VIOLA, the project VIOLA is organized as a consortium apart from DFN, who is the consortium leader. There are three industrial participants. This is Alcatel, T-Systems, and Siemens. And in addition, we have six participants from the research and university area. This is the Fraunhofer Gesellschaft, the former GMD in Burlinghofen, the Research Center Jülich, the Research Institution CESAR, the University Bonn, the University for Applied Science in Bonn, and the Technical University in Aachen. In addition, we have a so-called associated partner. This is Gasline. Gasline provides some fiber optic, some fibers to the project VIOLA. VIOLA has started 1 year ago. We have the project will last for about 3 years, and it is funded from the German Ministry of Science with about 11 million euro. The total cost of the project, including the contributions of the partner, is about 20 million euros. The major goals of VIOLA are located in the networking area, even if we have a so-called integrated project. We want to test and evaluate different equipment, different concepts in the routing and switching area, with special emphasis to signaling and management procedures. We want to test and evaluate all this in a wide area testbed, which is widespread over Germany. And in addition, we have a so-called laboratory environment for, let's say, short-time tests and special tests. Also special tests with maybe additional industrial partners who will provide some equipment for some time. Apart from a number of various goals, there is one major goal for VIOLA, especially from the viewpoint of DFN, that is to contribute for the preparation of the X-Wind. X-Wind will be the next generation of the German Wissenschaftsnetz. Last autumn, DFN made already a call for tender for fiber lines and for DVDM equipment, and just in these days, the implementation of the fiber and of the DVDM equipment has started. Sometimes around 2006, 2007, DFN will also implement new equipment in the area of routing and switching, and especially for that purpose, VIOLA will and should contribute some experience with the possibilities and capabilities of the equipment, of the state-of-the-art equipment. So the X-Win is a stepwise implementation, and VIOLA will, over the time, contribute some information to that. I have mentioned, and the name tells you already, that VIOLA is an integrated project. We have some, I must say, finally few applications at the top. We have a middleware area where we implement some middleware tools, and as a major part we will deal with a network area, especially with a control plane. The topology of VIOLA you see at the slide. The central triangle, the central cornerstone of VIOLA is located in the area of North Rhine-Westphalia. It includes 3 institutions. That is the Research Center in Jülich, the University in Bonn, and the Fraunhofer Institute also near Bonn. This triangle is interconnected with several 10 gigabit lines, and from that triangle we have further lines to the other locations in the area, the other user-oriented locations, University of Aachen, CESAR, and the University for Applied Science in Bonn. In addition, we have from GMD an extension to Nuremberg, to the location of T-Systems, that is in Bavaria. And from T-Systems there is an additional extension to the nearby University of Erlangen. VIOLA is also connected to Geong and to the current GWIN, of course, and we have some plans to extend VIOLA again to some further cities and locations, probably in the Bavarian area. Here you see, let's say, the central picture of VIOLA that shows you the equipment which is implemented in the various locations. In the circles, the circles represent the 3 center locations at the University of Bonn, in Jülich, and at the GMD. At each of these locations we have SDH switches from Alcatel, further router systems from Alcatel, gigabit Ethernet Riverstone switches, and at 2 of these institutions also some SDH switches from Siemens. The extension from GMD to Nuremberg leads finally to another SDH switch from Siemens Sycamore and another SDH switch from Siemens at the University of Erlangen. The other user institutions are interconnected via Riverstone Giga Ethernet switches. So, and the central triangle is interconnected with DVDM equipment with several times 10 gigabit lines. So we have the possibility to interconnect this variety of equipment via different ways. We might interconnect, for example, the Riverstone switches directly with each other with 10 gigabit. We might interconnect them also via the Alcatel SDH switches to each other via 10 gigabit lines, and we might also have, that means we, including the SDH switch here in Sycamore, the Sycamore SDH switch and the Siemens SDH switches, we have the possibility to have several different SDH domains, so to test not only internal SDH protocols but also external inter-SDH domain protocols like the EN and I. Within the triangle, I have mentioned already that we might interconnect the user via different procedures so that the end-to-end connectivity might establish via Ethernet connections on top of SDH or via Ethernet via a virtual private network with Ethernet. Here you find the major properties of the participating equipment. The Alcatel SDH switch is able currently to signal some parts of the GMPLS environment, and in addition first implementations of the UNI and ENNI from the optical forum. The Alcatel router is able to implement a VPLS or HVPLS environment. The Riverstone, of course, does the same. And the SDH switches from Siemens and Siemens Sycamore implement also various aspects of the UNI and INNI interface procedures. This picture shows you the architecture of the different components which might provide a certain kind of service. The applications on top of this have access always to an Ethernet service environment, and the Ethernet service environment may be adapted via generic frame procedures or via LCAS as a point-to-point Ethernet connections on top of the SDH environment, or the Ethernet service will provide will implement it as a VPLS, HVPLS service environment on top of the MPLS environment. So we have within the VIOLA very, very different possibilities to analyze and test, and even via the participating companies contribute to the specifications which are currently under development. We deal with the GMPLS environment. We will also deal with the ASIN environment that includes at least some parts of the IETF-defined GMPLS environment. And we will test also a number of interfaces which are defined by the optical internetworking forum. That means the UNI interfaces, the ENNI interfaces, and the INNI interfaces for the internal part. This gives us the possibility to have several interoperability tests and experience with the performance of all these interoperability environments. The provision of Ethernet I mentioned already will be realized via two ways, either with GFP and LCAS on top of SDH, or as an operated layer 2 subnetwork with VPLS based on the Riverstone and the Alcatel switches. At this picture you see the current topology that forms the VPLS or HVPLS environment. It is realized with the 3 Alcatel router systems located at the triangle I mentioned, and in addition with the 3 central Ethernet switches from Riverstone, and from these VPLS environment, we have some extensions to CESA and to the University for Applied Science, so we also could test the HVPLS environment. One goal is also to develop and implement, as in several other testbed environments, user interfaces, so that finally the users might establish an end-to-end interconnection. For these developments, we will also, of course, use the currently available MPLS environment, but also as the implementations go on, certain aspects and certain available results from the GPLS environment. Few words to the middleware. The middleware environment is implemented mainly with a Unicore software. The Unicore software is an ready for operation and stable operational software to interconnect supercomputers or PC environments. It has some interoperability to the Globus toolkit, and within our project there are some extensions and some additional portations are planned. Especially we will develop on top of the Unicore environment a meta scheduler based on the architecture developed in the Global Grid Forum. And another important aspect from the middleware environment is that we include certain analysis and test toolkits for distributed applications, so that we finally not only could have performance tests on the network level, but also performance tests on the application level at the end-user to end-user environment. For the applications, we have looked for real available existing applications, so we didn't want to have some fakes or just network generators in the environment, because the real life of real users is much more complicated as one could imagine. We have looked for applications with as high as possible transfer needs, and also with different needs for performance, for jitter, for quality of service aspects. I must say finally that it's not an easy task to find such applications. Everybody says, of course, we are interested on high performance networks, but if you are going into the details and looking what are the real needs of the applications, it's sometimes hard to find really high needs. But finally we got some. We had, because of funding restriction, even we had restrict the available applications to less than we wanted, but so we have chosen some applications which all of them provided the environment we asked for: high transfer, certain jitter needs, certain demands for quality of service, so that we have a variety of demands and may stress, let's say, the network environment from different aspects. Here you find some demands and some environments the application have. So we have up to, let's say, 6 or 8 gigabit transfer demands from the application. We have certain jitter and certain latency requirements. The applications are inside the different institutions are interconnected to VIOLA with Giga Ethernet. That means with several times of Giga Ethernet, starting from 2 times Giga Ethernet, for example, at the University of Aachen, to more than 30 times Giga Ethernet capability at the Fraunhofer Gesellschaft. Some information to the cost spread. VIOLA is finally a network-oriented project, so more than 80% of the funding goes into the direction of networking, and about 13% are reserved for the applications and for the middleware environment. The VIOLA project is a German national testbed environment. Of course, VIOLA, or the participants in VIOLA are interested also to interconnect the testbed and also the experience made in VIOLA with other international testbeds or experiences. And this is certainly fulfilled via different ways, and one is the participation of VIOLA participants also in other activities. DFN, for example, is participating in the EGE project, and several VIOLA participants, TSE, DFN, and the University of Erlangen, I mentioned not yet at the beginning, are participating in European testbeds like MUPBED or GN2. So VIOLA we see as a national basis from where we might contribute successfully to some further international projects. Coming finally to the current status of VIOLA. We started last summer, I mentioned. Around the beginning of this year, we finally finished the implementation of the equipment, of the fiber lines, and of the network management operational environment. And since then, a number of tests have started, especially in the work item of transport and signaling. Some interconnectivity tests, for example, with the ENNI interfaces between Alcatel and Sycamore have started. We have implemented the VPLS environment with Riverstone and Alcatel equipment, and we have started the specification and the design for the end-to-end user interface and to that area belonging reservation system. In the middleware environment, a first version of the existing tools is deployed and went into operation, and all the applications are also interconnected and have started, let's say, to stress the network environment. So finally our technical environment must now show that the equipment and what we have performed is ready to serve for the users. Thank you.
Okay, thank you very much. Okay, are there any questions?
You mentioned the meta scheduler in one of your slides in the middle, and I was wondering what are the functions of the meta scheduler that you mentioned and how it uses the infrastructure. You were talking about...
Ferdinand, I'm sorry, I have problems with my ear. Ferdinand, kannst du das beantworten?
Yes, okay, we can take it offline.
I have problems to understand you. Sorry.
The metascheduler will be used in order to reserve computing devices like PCs in the clusters, and it will also be used in order to reserve bandwidth, which will be used in order to interconnect the clusters.
Okay.
Any other question? Actually, I have a question myself. You mentioned the interconnection at 10 gigabit Ethernet between the Riverstone and the Alcatel.
Yeah.
Is that working today, or?
Working. Let's say we have established the test environment, and as I know, the first test between them has started. That does not mean they are ready for service.
Okay, but it's a GFP-based interface with post frames.
Who knows better?
Your question is about the GFP interworking between Alcatel and Siemens?
Yeah.
We will have tests about this in about 2 weeks. Currently, we are doing some preparations. Alcatel is changing their Ethernet interfaces for this test, so I guess at the moment we have some interoperability problems, but I hope then we start the tests in about 2 weeks. Then these problems will be solved so that we will have a successful test.
Okay, thank you very much. If there are no more questions, I would like to thank Peter Kaufmann. So the next speaker is Henrik Wessing from the Danish Technical University, and he's going to speak about the EU MUPBED project. You can switch.
Thanks, Olivier, and also thanks to Peter for the presentation on VIOLA. There'll be a lot of some kind of overlap also with this presentation. It's also from a European testbed, and I hope everybody is in good condition here. Just half an hour after lunch. I know it's a bad time to be on, but you're doing good. Okay, so what I'm going to talk about now is the European IST project, MUPBED, and I will focus mostly on the integration part of the applications and the network control plane. MUPBED is for multi-partner European testbeds for research networking. So a main motivation here is that considering we have a high demanding application over here, and we need to have some kind of bandwidth through this network. What usually happens is the application sometimes initiates at the client, and what our vision is that then it sends a request for the network resources, and the network respond by simply setting up the resources or allocating the resources that are required, whether it would be on a single domain over here or through several domains. So in this there are some things to consider. First is application to the network interface. In some way we need for the applications, which is not necessarily a user, because we had some discussions yesterday in the bandwidth on demand session about the users requesting some bandwidth. But here it's more like the applications, of course it's started by the user in some way, that are requesting bandwidth. So some way we should communicate the requirements from this specific applications that are running and down to parameters that the network can can set up resources upon. So that also requires a strict definition of what we are going to use for user network interfaces, also introduced in the last presentation, and network interfaces. Issues like multi-domain traffic engineering are also very important, but this will not be touched in this presentation because there will be a presentation on exactly this issue later today. I think it's by Jean-Marc Hughes from Juniper. And also, in order to make this relevant at all, we need to find out what are the application requirements for different kinds of application. Obviously, different kinds of application have very different kinds of requirements. It's some kind of flashing of the obvious, but well. So the agenda. I will just also mention how are the MUPBED project organized, the consortium and the objectives, and then looking to try to give an overview of the MUPBED testbed, show how it is interconnected, and also we are using ASON, automatically switch optical networks, and GMPLS as a way of switching in the testbeds that we are interconnecting. So I'll give a short overview of that, and then we'll turn to the application side and see what are the applications that we have initially selected for trial in the testbed, and the scenarios that we are setting up for testing these. And in parallel to that, we are also doing some modeling activities. The last two topics are the user community. We are having a collaboration with quite a number of user groups, and we'd also like to extend that. So that also has to do with the workshop that we are going to have on Thursday. So I'll make a little commercial for that. Okay, the European IST project MUPBED. We had the motivation before, so the main goals here, and I'll only take a few of them. But the two main goals are, first of all, to verify how can we make a ASON GMPLS control of a multi-domain optical networks, both with several, for instance, with several domains. And then also try to investigate what are the benefits when we are having a dynamic infrastructure. It's more like some kind of also on circuit on demand switching for very short time intervals. How dynamic should such an infrastructure be, or can it even be too dynamic? Will that have some negative impact? So derived from these, we have some sub-objectives, and some of it I have already mentioned. So, but we are focusing very much on research applications because we also believe, and I think this conference here confirms this very clearly, that the really high-end applications and very high demanding applications, we see them from the research communities. So it's our hope that also the MUPBED also, for instance, together with the VIOLA project, can help in introducing guidelines for implementation of ASON GMPLS technologies in European research infrastructures. The MUPBED consortium, and the project is a European IST IP project. It's 3 years, it's been running for less than a year now. Most of the time it's been used for the interconnection work, which can be more complicated than it looks as in the first glance. But we are a consortium of 16 partners from 8 countries: Denmark, Germany, Hungary, Ireland, Italy, Spain, Sweden, and Poland. So it's more like most of the European Union. And the partners here are, that's something. The partners are both equipment providers like Marconi and Juniper. It's telecom operators, so we're also including partners like T-Systems, Deutsche Telekom, Telefonica in Spain, and Telecom Italia in Italy. And then also the national research and education networks like Radiaris and DFN also. So let me here show you the initial reference structure that we are using in the MUPBED project. And I'm showing this slide also to emphasize what we are aiming much is on the integration. And I mentioned this, the horizontal integration between different network domains, different NNIs to be defined between these domains, and how to do this multi-domain traffic engineering and these things. But also on the more vertical integration. We have our, in a way also to define a resource for communication of the application requirements down to network control plane. So here we are at the MUPBED testbed. We have 5 larger European testbeds. In the northern region we have the Acreo, it's in Sweden. It's a GMPLS enabled testbed, which is and here locally. It's a PSNC, this is an Ethernet based our eastern testbed. And T-System is hosting an ASON GMPLS enabled testbed, we call it the central testbed. And the southern testbed is also ASON GMPLS enabled, hosted by Telecom Italia. And Telefonica is hosting our western testbed. These testbeds are we now connecting with different links, mostly gigabit Ethernet, through the NRENs and also through the CERN network. So also included in the as partners are most of the NRENs that are listed here. So coming back to this interconnection that is set up, these are the links that, as to my knowledge, are the way it is established by now. And I can mention that for just a few days ago, this link from DTU to the Acreo was up and running, so that's also quite nice. I think most of the connections are now up and running. That's, however, to my knowledge, still there are some problems in the western testbed with the interconnection. And this provides this logical testbed that we can now use and then define our NNIs in between. Yeah, I think I'll just go further on, but this is the picture of the testbed as it is and should be. So I mentioned before that we are using ASON GMPLS, and we've been mentioned this a couple of times, but it might also be a good idea to say why are we doing that, and also as Bob Riddle mentioned yesterday in the bandwidth on demand session, setting up a path through a network and a network segment usually requires a huge amount of emails and phone calls, and it's a quite cumbersome process. Mostly, and the policing is mainly based on who knows who, and yeah, that's and that kind, and that's of course takes time, and within ASON it defines some. There are defined some. And also in the related work at OIF, there are defined some interfaces. For instance, a UNI interface between the client and the network, in order that the client itself can request for resources and a path establishment. And also for routing further on, there are defining the NNI's network interfaces. This allows for a much more simple network management in order to, because of most of the routing and signaling functions are then moved to the control plane instead of networking plane. Instead of management plane. So let's coming back to this proposed reference architecture. Having here these applications that we have selected in the first place, and we're operating with a number of different planes. Of course, the application plane with the applications, but also within the network, we're having both the control and database, of course. And I would even move on now and say this communication, that's some of the very key issues in the project, is the communication from the applications and then down to the network, and how should that be done. We are working with two different models. First I will show you here, which is shown here, the UNI model that we call it, where the responsibility of setting up the path is on the client, on the application side, which is at the application side an adaptation function translates the resource request from the applications and then into the something that is understandable by signaling protocol like RSVP and to set up into the network. So, because also, again, at this point here, we like our application requirements written in something that is understandable by network, that is delayed, jitter, its bandwidth. I know very well that also that was mentioned in our first plenary speech, that from the application side, then the network should just be very responsive, and when I hit the enter, then things should happen. But both things are extremely important. So that's one of the models that we have been also are examining, where these most of the functionality is moved to the application side. Secondly, the API model, where the adaptation function is located at the responsibility of the network. So the applications more or less simply sends some more abstract requests, and these are translated on the network side. So that also means that the specific resource requests are generated within the responsibility of the network, and it appears most of also the telecom operators, which are a little more conservative than usually NRENs, probably seem to have a little slight preference of this one. That means that policing, AAAs and so on goes on in this adaptation layer. So let's move the focus on to the applications that we are using and trialing in the testbed, and most of the experiments are first now begin to come up and running in a larger scale, because we have had problems with getting the interconnection up and running. So one of the applications is high quality uncompressed video transport, and considering that, I think that's one of the killer applications, and at least at present time. Considering a studio with the remote cameras in one place and then an online editing function in another part of the testbed, in that case it's very important that the editor can react fast to what is going on. So it has been shown that latency is much higher than 150 milliseconds will not do simply. And that means that it will not be possible to make compression. And again, that for each camera, this will require 300 to 600 megabit per second at least, also depending on overhead and error control. So another of the applications that we are looking into are video conferencing, especially from our partners at Telecom Italia and Telefonica, setting up some both point-to-point and also multi-point video conferencing. And of course, for video conferencing, the latency is extremely critical. We all know I don't know, everybody knows, but it's the very irritating about talking in a satellite phone, and this response time is very long. That's something that's really annoying. So also the constant storage are also one of the applications that we are discussing, and also grid. And grid is really a buzzword also in this at this conference here. The setup for grid that we are using is quite a simple one. It's for setting up for virtual organizations, and I have one slide on that as well. And of course, also the grid can be used for very high bandwidth applications, as has been discussed in several sessions during this this conference. Taking an example of one of the test scenarios that are used for the that's from our TI lab. It's test scenarios built on if you have a very large file that should both be compressed and signed and encrypted. So trying to find out what happens if these different functions are placed in different locations. What are the performance seen from a user perspective, and also trying to translate this into what are the requirements by the network, and can we for this file transfer so on setting up some partner, will that be helpful, and how much, and also how much time does it take to do this setup and so on. So these are issues. In parallel with their experimental work, we're also doing modeling activities, and the reason for doing the modeling activities are, of course, in order to is not as result in itself. It's when we have the result from the experimental works, then the modeling is a very good tool in order to see what happens when we scale things into not just in the MUPBED testbed, but also for a more global scale. The testbed is, of course, a testbed, so it is for giving some clues on what is going on when this is deployed, or if it should be deployed. Some of the modeling is on 3 stages. First, as application modeling, where we see, okay, the application that we have, they should more or less learn models that makes the same network behavior as the applications, at least comparable, and see for a reference situation. And then also what happens when we then implement some, first of all, static traffic engineering, and then, as shown here, implementing these network resource request and network resource provisioning from the network side. So that means that that we can try to see, okay, and also fine tuning whether what should be triggering the application, the resource setup. Should it be based on an explicit request from the application, or should it be based on now we have a huge amount of data going in this direction, maybe it's a good idea to set up a specific path. So this should be whether it's triggered in what way, and if it's the last one, when should the triggering go on. As a little funny thing, and that leads to my last points, is that the OpNet modeling that we've been doing really reflects, OpNet is the tool that we're using at the DTU. It really reflects the traditional way of thinking in network. For instance, setting up the label switch path in the network in the MPLS model is completely a separated process from the applications in any way. And that also considers that this setup is a telecom world, and the application is just something that are going on through these links. And from the application side, then more or less that the network is that's just getting these applications transported. So in order to work with these things, then it's really important to make a lot of modifications to standard models. So, but the funny thing is here that it is the traditional way of thinking that are in fact being a little compromised, but by such project also, I think by other bandwidth on demand project also. We are doing a lot of collaboration with different user communities. I could mention here the Polytechnic of Torino, IRT, UPC in Spain, and also University of Copenhagen, and the list is not exclusive. There are a number of more that we are collaborating with. But also I would like this list to grow even further. So if any of you, if any of things that are missing here, or applications that think that where it could be very useful to trial it in a testbed like MUPBED, then please let me know. The application that we are using is now in new and not yet deployed distributed applications. Some of them are also deployed, but we're making some further testing here. But any applications that could be interesting, then we could be very interested in also some further collaboration. So what we can offer is availability to a testbed. So something, then please let me know. So the code word I will use for this MUPBED in total is, this is more as some of my last slides here, are integration. So we're trying to have what I will call a holistic network view, and that means that we have integration, horizontal integration. I've mentioned that on an ASON GMPLS scale. How can these techniques work together? And also integration on a common control plane. But then vertical integration, definition of the communication channel for resource request into the network control plane. And last but not least, the human integration. We are discussing two different words, and we have within our meetings in the project, we can easily see that this is happening. We have a telecom world who thinks about application as bits that has to be transported, and then all the computer science world that considers that in the network it should just be there and do things. So we have these two network perspectives, and it is so really important also to reach a common understanding of things, and common understanding of the application requirements to the network, and also what can network in fact provide. So therefore we have also a short, not a short, but a MUPBED workshop Thursday. I would kindly invite all of you. Please in that case let me know, because that might be a good idea if we should organize some lunch. There are no lunch officially Thursday, so that was a little motivator. The agenda for this workshop will be a short introduction to MUPBED for those who are not here, and then there will be a discussion from the application side again from the grid motivated by VIOLA and DASA projects by Ralph Niederberger, and Robert Mayer from PSNC will also give a presentation on very high demanding applications, and then there will be a streamed a presentation from Aphrodite Sebasti from Jean. See what can they provide now on bandwidth demand. So it is, some of these have been also discussed at other parts here at the conference, but the idea is here to also have a forum for more open discussions. So it is this in the conference center Thursday at 2 o'clock, probably in this in room E, and let me know, this would be helpful. So a summary. I think I have said everything, but that's also the point of a summary. The motivation, dynamic resource allocation, and also the investigation of multi-domain ASON issues, and also try to find out what are the requirements of the applications today, seen in what we call it terms that are understandable by networks. The MUPBED testbed comprised 5 larger European testbeds interconnected through the network, in the NVENS and the CERN, and we are focusing now on 4 different application groups, and in parallel to this we are doing modeling. Collaboration with user communities. If there are things that are not covered, or things that, well, I have an application that could really be useful to test in a testbed like MUPBED, then please let me know. And again, we have the workshop here. So that's basically my half an hour this introduction to what MUPBED is of a kind. Of course, the number of details are in some sense reduced in such a presentation like this. Thank you.
Okay. Is there any questions?
And you're welcome to ask questions, of course. I can see if I can answer them.
Well, it's a very simple question, really. Are you planning any demonstrations of this application, triggered LSP setup, at, say, a meeting like iGrid or supercomputing?
We are planning a number of demonstrations. There has already been some demonstration at the of some of the application, at least at the VIOLA workshop in Berlin. I think it was one. But also, to my knowledge, there's also a demonstration being planned for the BRED conference in Bordeaux this year. But and then there are also some. I don't remember all of the demonstrations that are. We have one work package that are mostly working on demonstrations. So, so of course this is in the scope of the projects to do all the dissemination that is ever possible, especially when you have such a large physical network.
Any more questions? Actually, I have one question. Are you satisfied with Giant 1 MPLS service, and do you plan to make use of the new Giant 2 end-to-end capabilities once they become available?
Well, we are always interested in using the best infrastructure that are available, of course. So so we are also working quite close to see these issues. I know also that some of the POP will be removed, so the Xiang 2 will have some effect on MUPBED anyway. But as it is new with the interconnection, then we are doing the switching in the testbeds, and then the Xiang network is basically used for making tunnels. But of course, we'll constantly look into things. But I think that's what I can say about that.
Okay. Seems to be no other questions. Okay, so let me thank you again for the presentation. So the last speaker is Sergey Ten from Corning Corporation.
Hello? Hello? Do you hear me? Do you hear me? Thank you, Olivier. And my name is Sergey Ten. I'm going to talk about optical fiber development for high data rate transmission. And this topic is totally different from what you heard so far. It's about a component. So far we talked about networks, about devices like switches. This is about component, but that is probably most important component of the network. It's optical fiber. And this is actually relatively not so old product. It's 25 years since low attenuation optical fiber has been invented. And what I want to show in my talk is that although people think about optical fiber as a ubiquitous component frozen in time, actually it's not. It's a component that constantly evolves, and the evolution of this component is driven between the synergy between development in transmission networks and the new capabilities of fiber making. Let's look at one of the most important fiber attributes that were defining the evolution of fiber, data rate. I'm going to limit my discussion in this talk to long-haul networks. And in these networks, SONET SDH transmission gear is deployed. And historically, SONET SDH data rates quadrupled. And this slide shows time of introduction of the particular bit rate. And you could see that until recently, the data rate would quadruple about every 5 years. So the next data rate in this, on this chart would be 40 gigabit per second, and it's been more than 5 years since 10 gigabit rate was introduced. And I'm going to discuss why we think 40 gigabit will be introduced and what are evolution in fiber that would help to enable 40 gigabit systems. So I want to talk about 3 major things in my talk. First is what are the drivers for 40G. Second is what are the improvements in fiber attributes that facilitate 40G introduction. And then I'm going to talk about new fiber concepts that probably you may not have seen that would make 40G transmission even more cost effective. And then share with my answer to the question, will we stop at 40G or not? Okay, very quickly, drivers for 40G. It's been a growing evidence that network operators, mostly in order to reduce their cost, would like to have a packet switched core. And in order to enable this vision, you need powerful routers in the core network. And there is a discussion what powerful means. Cisco released in about May of last year, Cisco Carrier Routing System 1. This is a very big router which is capable of scaling to 92 terabit per second of switching capacity. And Cisco argues that they need this scalability in order to make this investment in the switch long-term investment that that network operators traditionally saw from pieces of equipment like a class 5 switch. So in order to achieve this very high switching capacity in the reasonable footprint, which would fit into the building, Cisco decided to go to 40 gigabit per second interfaces. And actually, in the room F, in this conference, you could see the demo that Cisco runs, and you could learn more details about this router. So immediately after Cisco announced that this router is commercially available, number of networks, especially in North America, rushed to demonstrate that their backbones are actually compatible with 40 gigabit transmission. For instance, this slide shows demos that MCI reported at OFC of this year. OFC, it's Optical Fiber Conference, the biggest conference on fiber optic transmission. So MCI reported that they performed 1,200 kilometer field trial over existing link using existing WDM system, which ran at 10G, but was upgraded to 40G using transponders from startup Mintera Corporation. And I showed on this slide, courtesy of Mintera, the picture of this transponder. It's, of course, thicker cards at 10 gigabit per second, but it's not as thick as 4 10 gigabit cards. And that's a whole value proposition that you will see some increase in the cost and the size of the 40 gigabit card, but it's still less than 4 times 10 gigabit cards. So they demonstrated successfully error-free transmission at the distance of 1,200 kilometers at 40G, and by any means, that was an impressive result. Okay, so let's talk about how improvement in the existing fibers facilitate 40G introduction. And first of all, I'd like to define more rigorously what I'm going to talk about. I'm going to talk about long-haul systems. And the picture of this long-haul system you see on this slide, basically we're talking here about WDM, long-haul transmission system, which typically propagates signals from 500 to 1,500 kilometers with the span length. Span length is the distance between amplifiers, which is usually go from 80 to 100 kilometers. So in these systems nowadays, typically people use 10 gigabit per second. It's a predominant data rate. And there is a standardized frequency grid called ITU grid. And common grids use now 100 gigahertz and 50 gigahertz channel spacing. So the band of choice is so-called C-band or conventional band, which goes from 1530 to 1565. And that is because very efficient erbium doped amplifiers available for this wavelength band. And typically modern erbium doped amplifiers, they have 2 stages to accommodate compensating device, which I'm going to talk about later. So let me support my statement that fiber innovation has been driven by the innovation in transmission systems. And this chart shows the brief history of fiber innovation in conjunction to the changes which happened in the transmission systems. And if you could see at the beginning of 80s, first transmission systems used 1310 nanometer wavelengths because that's where sources were available. And that time, so-called standard single mode fiber was developed. This fiber has zero dispersion at 1310 wavelengths. And let me remind you what dispersion is very briefly. Dispersion is a property of fiber that basically leads to spreading of the pulse. And the spreading depends not only on dispersion, but on the length of the fiber. So the higher the length of the higher the dispersion, the higher the length of the fiber, more spreading, more signal distortion you would have in your system. Then system designers realized that, wow, the lowest wavelengths for the lowest loss in optical fiber occur actually not in 1310 nanometers, but it occurs at 1550 nanometers. And they start designing systems over there, and fiber designers helped them by developing fiber which would have zero dispersion at 1550. So you could see the synergy here, fiber designers helping system to achieve their goal of achieving longer distances and longer distances between the amplifiers. And then in the beginning of 90s, so-called non-zero dispersion shifted fiber was developed. The reason for development of this fiber is very curious. After people switched to 1550 and start using efficient erbium amplifiers, they realized that actually you need very small dispersion, not very small, some finite dispersion to suppress bad nonlinear effects that occur in the fiber if WDM channels are spaced exactly on the ITU grid. So the next generation fibers would have smaller dispersion than standard single mode fiber, but finite dispersion to suppress these nonlinearities. So we're now here in the mid of 90s, and I'm going to talk about what are the improvements in fiber attributes we would see now to facilitate 40G. Okay, let me show you what are the fibers that you would find deployed mostly in Europe and North America. Broadly, they can be divided into two big categories. First category is standard single mode fiber, or so-called G652 fiber. And the word standard is actually just the name, because other fibers belong to some other standards. So it's not like other fibers are not standardized. The major requirement for this standard single mode fiber is to have zero dispersion around 1310 nanometers. So that's a requirement for this fiber. The other class of fibers, so-called non-zero dispersion shifted fibers, these fibers have lower dispersion than standard single mode fiber at 1550. And actually dispersion is defined to fit certain requirements that is called in the slang dispersion box. So the dispersion box for the non-zero dispersion shifted fibers is shown here. And in this table, you would see the typical parameters of these two class fibers deployed widely in the world. The main attention I would like to attract you to the fact that standard single mode fiber at 1550 would have dispersion about 17, whereas non-zero dispersion shifted fiber has dispersion from 4 to 2 times lower than that. Okay, now let's talk about what are the challenges that system designers face when they would go from 10 gigabit to 40 gigabit per second. First challenge is that historically was a challenge when people went from 2.5 gigabit to 10 gigabit was so-called polarization mode dispersion. And I'm going to show you that the modern fibers are made now actually have such a low PMD that it won't be a problem for 40 gigabit per second. The second challenge is that going from 10 gigabit to 40 gigabit, you need to achieve higher signal to noise ratio. And there are a number of techniques actually in electronics that allow you to overcome this challenge, such as forward error correction, FEC, or different modulation formats. I'm going to talk about another technique which uses transmission fiber as an amplification medium to increase the signal-to-noise ratio at the end of the link, and that is the Raman amplification. And I show you that fiber attributes can be improved to improve Raman amplification properties. And finally, I'm going to talk about new concept of the fiber in the context of precision compensation. And unfortunately, the precision with which you have to compensate dispersion of the link grows as a rate squared. So you need to actually improve it 16 times, not 4 times, when go from 10 gigabit to 40 gigabit per second. So let's talk about polarization mode dispersion, or PMD. If fiber were absolutely symmetric, you would have 2 degenerate modes. You would have 2 polarizations in the fiber which would propagate with exactly the same speed. So if you launch a pulse with polarization along any axis, you would have exactly the same time of propagation. Now, in reality, fibers have slight asymmetry acquired either in the manufacturing process or when they are put in the cables and deployed in the real network. And this causes birefringence. Birefringence is a phenomenon when you have one propagation time when light is polarized along one axis versus another propagation time when it's polarized over other axes. And the delay between these 2 pulses is called differential group delay. Now, polarization mode dispersion is a more complex phenomenon than just birefringence. Actually, PMD is a phenomenon when this differential group delay changes with time. And to characterize this, always changing DGD, people introduce PMD, which is typically measured in picosecond, and PMD is an average DGD. Fortunately, for fiber makers, PMD grows only as a square root of length. It's not linearly proportional to the length of the fiber. And the coefficient of proportionality is called PMD coefficient, and measured in the picosecond divided by the square root kilometer. So how does PMD affect transmission? This chart shows power penalty induced by certain DGD on the transmission. And you could see that really the scaling factor in this penalty dependence is the ratio of DGD to the bit slot. So the rule of thumb is that if your DGD reaches third of the period of the bit, then you would have a noticeable penalty in your system. And remember that PMD is a fluctuating DGD. So to make the design of the system safe, people came up with this rule of thumb that PMD of the link should be less than 1/10 of the bit period, which means for 10 gigabit per second that it is less than 100 divided by 10, which is 10 picosecond, and for 40 gigabit it would be 2.5 picosecond. Now let me show you that PMD of modern fibers is not a problem. There is a paper published at the last optical fiber conference by Level 3, who is one of our sponsors, where people from the R&D department of this network took an unprecedented effort to measure fiber attributes in their network. This network is built relatively recently, and they started building it in, I think, 1998. They use Leaf fiber. Leaf is a NZDSF fiber from Corning, and they deployed nationwide network. They also are present in Europe. And this chart shows PMD measured in this network. And the average PMD coefficient measured in this network was reported to be 35,000 picosecond per square root kilometer. Now, this paper also shows other attributes. So if you're interested, you could look in the paper. But if you take this PMD coefficient and use this rule of thumb that I showed at the previous slide, you would see that up to 5,000 kilometers, PMD will not be an issue in this network. So PMD is sufficiently low in modern long-haul fibers and allows to enable 40G transmission. But the key in the last statement is in the modern. Actually, PMD in the fibers made in the beginning of 80s was very high, maybe very high. Not necessarily, but maybe very high. And people saw many difficulties to go even from 2.5 gigabit per second to 10 gigabit per second. Let's talk about Raman amplification. What is Raman amplification? Raman amplification in its implementation is a fairly simple thing. Basically, you couple high-power Raman pumps in the direction contra-propagating to the signal. And through nonlinear effect called Raman scattering, these pumps cause amplification. Let me show you in spectral domain what you would see. When you launch, let's say, this pump, you would see the gain due to the Raman effect separated by about 100 nanometers if we target amplification in the C-band. Then what we could do, we could launch another pump and create an almost exact replica of this gain line, but shifted by the same shift as these two pumps are shifted, and so on and so forth. So you can construct whatever gain you would like to construct, and to make it even flatter, you would design so-called gain flattening filter and cut the ends of this gain ripple. In the simplistic language, how you can present Raman amplification, you can say, well, it's sort of the same laser amplification, but the upper level is where photon is absorbed is the virtual level, and then it goes to this level by emission of optical phonon. So this phenomena was known for a long time, and only recently it was start being used in the real networks only because the semiconductor pumps, which are sitting in this box, became powerful and became available for the reasonable cost. So why Raman amplification is good? The short answer is because it improves optical signal-to-noise ratio. So if we look at the signal, how it would propagate as a function of distance without Raman, on the dB scale, it would be a straight line like this. If we launch Raman pump, which propagates, as I said, from the opposite direction, you would see it also decaying like this. But the signal, which is launched now in the forward direction, would experience gain in the area where Raman pump is high, and you would see that at the input of the erbium amplifier, you would have higher power. And we know from radio physics that the higher the input power on the amplifier, the better signal-to-noise ratio. So that's basically the physics behind why signal-to-noise ratio is improved with Raman, and distributed Raman amplification typically improves OSNR by 3 to 5 dB. Now, it's a pretty complicated slide. I try to show you how gain depends and noise figure of Raman depends on the fiber parameters. And if you look at the formula for the gain, you could see sort of that it's inversely proportional here in this ratio to the attenuation on the pump wavelengths. And basically, the better attenuation, the higher the Raman gain. But the expression for the noise figure is totally incomprehensible. So you have to believe me that the noise figure improves, means becoming smaller if you have better attenuation at the Raman pump wavelengths. So this is the takeaway from the slide. The lower attenuation at the Raman pump wavelengths, the better the fiber is. And if we look at the fibers, again, from its inception till now, the first fibers actually had so-called water peak. Water peak is an elevated attenuation in optical fibers at wavelengths of 1383 nanometers, and they're attributed to the OH group, which is created in the silica cladding of the fiber. And this slide shows what problem this water peak creates for the Raman amplifier designer. Basically, you can have fiber with relatively low water peak, or you could have fiber with a relatively high water peak. And Raman gain and noise figure would depend on exactly which fiber light propagates in. For the fiber with higher attenuation, with higher water peak, you would see that the noise figure looks like, that the gain would look like this. It would be reduced, and the noise figure would be higher, which means it would generate more noise in the amplification process. So that's been the problem. And again, through years of manufacturing expertise, we learned that you actually can suppress this water peak. And as of this year, Corning NZDSF fiber called Cliff was released with a new upgrade. And this upgrade is a low water peak, which means that the attenuation at 1383 was reduced below 0.4 dB per kilometer. Moreover, in order again to facilitate the design of the Raman amplification, Corning introduced two more specifications at wavelengths of 1310 and 1450. And other fiber manufacturers do the same thing, so it's not only we. It's basically a common trend now in the industry to go and spec the fiber not only in the transmission band, but also in the Raman band. And again, with the purpose to help designing Raman amplifiers if they are needed in the network. Finally, let's talk about new fiber concepts that you may not have seen before. Let's first again remind what dispersion does to the system. Dispersion spreads out the pulse. And in this reference, we could see the parameter that is a product of distance, length of the fiber over dispersion, and how it depends on the bit rate. And this accumulated dispersion results in the 1 dB penalty. And if we calculate what this L times D product is, we would see that for 10 gigabit per second, it's equivalent to 60 kilometers of standard single mode fiber. Basically, you can propagate 10 gigabit signal over 60 kilometers and still have only like 1 dB penalty. Now, because at 40 gigabit per second, this dispersion penalty scales as a bit rate squared, you would be able to only propagate 3.8 kilometers. You see how dramatically smaller this tolerance is for higher bit rate. Now, in order to get some reasonable transmission, even at 10 gigabit per second, we need to do something with the signal. And so far, a very effective technique was optical dispersion compensation. Optical dispersion compensation is basically based on making fiber that has dispersion opposite to the dispersion of the transmission fiber. And in this way, pulse spreads out, but then when it enters dispersion compensating fiber, it actually goes back to its initial shape. And you can recover basically dispersion penalty. And the first generation of dispersion compensating fibers were so-called flat. It's a slang which we would use. So flat refers to the dispersion characteristics as a function of wavelengths. Now remember that dispersion of all the fibers that are used in transmission have this positive slope. So if you try to take fiber which has positive slope and compensate it with the fiber which is flat, you would have residual dispersion that is looking like this with a red dotted line. So what it means is that only in the center of your channel plan you would compensate dispersion well. At the edges it won't be as good. Now the concept of slope compensating fiber is shown in this slide, and basically through lots of pain, that's probably the most difficult fibers to make, slope compensating fibers. We designed fibers that have not only negative dispersion but also negative slope. So when you add these two fibers in the right length ratio, you would get residual dispersion, which would be 0 across the very wide band of wavelengths. So with these fibers, you can enable precise broadband dispersion compensation, and that means cheap. You compensate all channels simultaneously, which means you divide the cost of this unit over all the channels that you're going to deploy in your network. Now let me just show how the picture looks like from a slightly different perspective. If you are able to track dispersion of the red channels and the blue channels, you would see that red channels would go up and up and up if you compensate with the flat dispersion compensation. Let me show. Again, if we take red channel, which is here, it has residual positive dispersion, and dispersion here is negative. So if you track dispersion of blue and red channels, you will see that they go in the opposite direction. And actually, with the flat dispersion, you would still will be within the 10 gigabit tolerance, because that's what for these first generation compensating modules were designed for. But they would spread out for the distance, for the dispersion higher than it's required for 40 gigabit tolerance. So you would need to go and compensate each channel separately, which for 40 gigabit would be equivalent to per channel compensation and increase the cost of the total system. So if you use slope compensating DCMs, you would have exactly the same dispersion for the red and blue channels, because you compensate them both to 0, and you will be able to bring all the channels within the 40 gigabit dispersion tolerance and enable broadband compensation of all channels. So these compensating devices have been sold now for probably more than 10 years. And based on all this work, we came up with a more revolutionary concept called dispersion managed fiber. And in this concept, you actually place a transmission fiber and compensating fiber in the cable. So you have everything, in the ground and the cable, and you effectively see from the side, from the amplifier huts, span with very small total dispersion. And there are many reasons why, for the terrestrial networks, you would like to sandwich the negative dispersion, negative slope fiber in between of the positive dispersion fibers. Some reasons are that if you have higher power here, typically you have lower nonlinear effects in the larger effective area fibers, and that's why you would like to place this fiber here. So what are the benefits of this dispersion managed fiber? This slide shows most obvious benefit, and that is simplification of the transmission system, and this simplification would lead to the improvement in the optical signal to noise ratio. Basically, if you use single fiber, you would have to, as I described, introduce dispersion compensating module, which would be sitting inside of the amplifier. And with dispersion managed fiber, since dispersion is compensated in the transmission path, you could have very simple amplifier with one stage, and the simpler amplifier, the lower noise it generates. So at the end, you will have less noise in the DMF system than in the system with single fiber. So instead of going through mathematical formulas and prove you that DMF has superior nonlinearity and et cetera, I'd like to show you a compilation of our results of HERO experiments at the OFC and ECOC conferences. OFC and ECOC conferences have this post-deadline section where everybody tries to write his name in the history by showing the largest capacity, the longest distance, or both of the above. And what we do, we track the HERO results and plot it in different dimensions. So on this chart, you would see capacity times distance product reported in these HERO experiments as a function of air. And that is reported for 3 different fibers: for the dispersion managed fiber, for standard single mode fiber, and for non-zero dispersion shifted fibers. And you would see that improvements in transmission would bring capacity distance product up for all the fibers, but dispersion managed fiber remains the champion so far. And since we don't have time, let me skip this, and I'm gonna go directly to try to answer the question, will we stop at 40 gigabit per second? Again, this is the chart from our tracking spreadsheet of these hero results. And now we plot what are the reported bit rates in the experiments, in the hero experiments, as a function of year. And these experiments could be transmission experiments or demonstration of the very fast transmitter receiver. We could see that here, between 2002 and 2003, sort of was a dead zone, probably after telecom bubble burst. But what is maybe not surprising but encouraging is that last conference in Europe, ECOC is a European conference, we see this splash of activities in the high data rates, and as high data rate as 720 gigabit per second was reported. Now, 40 gigabit per second is here. This point is interesting. This point is 160 gigabit per second. At this conference, they reported France Telecom in collaboration with, I think it's T-Systems and Alcatel. They reported 160 gigabit per second field trial over the France Telecom network. So clearly somebody is thinking about data rates beyond 40 gigabit per second. And finally, if you go to the Cisco demo, you will see in the slide demonstration that in their materials they say, hey, our router is actually taking 40 gigabit cards now, but we reserve to put even higher data rates in this router. So with that, I'm finishing, and the main idea which I'd like to tell you today is that fiber, as any other subsystem and networks, they evolve with time. And when you look at the fiber, you will see that its attributes improve, and there are more revolutionary concepts of fiber. And the purpose of this is to enable higher and higher data transmission rate and improve transmission and cost properties of the systems. Thank you.
Many thanks for this very illuminating presentation. There's actually also a lot of optimism, and I think in our community we are all looking for very high data rates. So it's very interesting. I think we can take 1 or 2 questions before we close. Victor?
Okay, I'm glad that 40 gigabit is not the end, so that's good to hear that. I have a totally different question. I think you didn't say that, but I think delay is another thing where we are bothered about, and I hope I'm not wrong, but otherwise people can laugh about me. I thought that the speed of the propagation, let's say the propagation delay in glass is 60% of the, or the other way around, of air. Is there progress in getting faster propagation or lower propagation delays in fiber? Because we can gain 40% of propagation delays there.
Okay, let me repeat the question in different terms, and then I try to answer. So the question is the following. There is a refractive index in the fiber, which is about 1.4888, so something like this, which slows down the speed of light from vacuum speed to something, as you said, 60% lower. And the question is there any effort to make the fiber which would get back the 60% in order to improve the latency in the network. Is that right?
Yeah.
So we looked at this, and I would say that in the conventional fiber design, it's very difficult, if not possible. However, there is a whole area of so-called photonic bandgap fibers that is being developed that actually promise to have attenuation even lower than what is achieved so far, 0.2 dB per kilometer. But this fiber actually would propagate most of the optical mode in vacuum, and it would have specially designed glass structure around it to support the optical mode. And I don't remember exactly what the effective refractive index is in these fibers, but I believe it is closer to the vacuum than to the glass. So, if these fibers are developed in some point in the future, you would get the 60% back.
Okay, last question.
For what distances does it make sense to use electronic dispersion compensation instead of the dispersion compensation in the fiber?
For what distances it makes sense to use electronic dispersion compensation? So let me give you a little bit background to the question. That I talked about compensation of dispersion using optical modules. There have been reports, especially like in the last 6 months, that you can compensate dispersion using tricky electronic processing. And there have been reports at the last OFC, again in this HERO post-deadline session, that you could go incredible so far distances, like 50,000 kilometers. Is it 50,000? Something like this. Kilometers without electronic dispersion compensation. My answer to this is the following, that we are in the phase where network designers not only look at the technical capability of particular technology, but they also look how much it costs. I mean, bandwidth is free, but somebody still has to pay for this, right? And the main question remains is that I think on the technical level, there is more and more confidence that electronic dispersion compensation is a real thing. It's not a fluke. But the question remains is how expensive it is compared to this conventional, proven, and deployed optical dispersion compensation, which works anywhere in the world right now. So that's a question that industry needs to answer in the next, probably couple of years.
Okay, I think we have to close now. So I would like to thank all the speakers for their very